Hello everyone, welcome back. This is Easy Learn AI. Today, we'll look at gradient descent, which is important to know in neural networks. Chapter 1. What is gradient descent? The basic definition of gradient descent is: what's gradient descent? It's a way in machine learning and deep learning to find the best settings for a model using a loss function. Here, when we say model, we mean a neural network. And parameter means things like the weights and biases in the artificial neural network. In our last sessions, we mostly talked about updating weights. So we didn't cover biases. But biases are also important in artificial neural networks. Biases help shift the activation function left or right, helping the neural network learn faster. For instance, if for some reason, most input values are to one side, shifting the sigmoid function to the left makes learning easier. This is because, as we saw in our last video, the curve becomes steeper. So, biases help the neural network learn faster. Back to the main topic. There's a new term here, loss function. The loss function is one of the very, very important ideas in neural network learning. Simply put, the loss function is a function that measures the difference between the predictions and the ground truth of the neural network model. This is a lot like the error concept we learned in our last video. If there's a difference between the model and predicted values, the sum of the errors can be shown as an area. Neural network learning is all about reducing this error by slightly adjusting all the parameters over and over. So if the model predicted like this, the sum of the errors can be updated like this. Similarly, when shown as an area, you can see the area, sum of errors, has decreased. So, making this loss function value as small as possible is a very important concept in neural network learning. To understand gradient descent, we first need to know more about this loss function. Chapter 2, Loss Function. As mentioned earlier, the loss function is about the difference between real and predicted values. There are many loss functions, but a well-known one is MSE, mean squared error. The formula looks like this. It might look complex, but it's very simple. MSE starts with the basic concept of the loss function, the difference or error between the real and predicted values. Since either the real or predicted value can be larger, to get rid of the plus and minus effect, we square the difference. Then, we add up all the errors for all data and divide by the number of data to get the average. So, MSE is the average of the squared differences of errors. Simply put, think of it as the average difference between real and predicted values. If the loss function value is big, there's a big difference between real and predicted values. If it's small, the difference is small. And smaller is better. Apart from MSE, there's MAE, mean absolute error. MAE is like MSE but uses the absolute value instead of squaring because squaring can distort small errors. Another type of loss function is the cross-entropy loss function. The formula for the cross-entropy loss function is this. Cross-entropy is an important loss function commonly used in deep learning, so I plan to explain it in a separate video. But for now, I want to say that compared to MSE, cross-entropy has the advantage of faster learning. The details will be covered in the cross-entropy video. Chapter 3, Gradient Descent. Now let's really get into the gradient descent algorithm. The concept of gradient descent is surprisingly simple. Let's assume we're using a loss function, MSE, as an example. To make it easy to understand, let's think of the simplest case. When n equals 1. When we replace all n with 1, the loss function becomes a familiar quadratic function. This lets us draw a graph like this. It's easy to see where the error is smallest. It's right here. While human eyes can spot this minimum error point quickly, sadly, machines can't. But there's an important discovery. The point where the error is smallest always has a slope of 0. So until we find a point where the slope is 0, we gradually reduce the slope. This method is called gradient descent. In linear functions, the slope is defined like this. Similarly, in nonlinear cases, it can be found with small changes in x and y. Once we find the slope at a point, if the slope is negative, we increase x. If the slope is positive, we decrease x. And if the slope is big, we make a big change. If it's small, we make a small change. This way, we're looking for an x where the slope gets close to 0, which is where the error is smallest. But you might say, in the case of MSE, the loss function is just a quadratic function. Can't we find the minimum value using something like the quadratic formula? Maybe you think like that. But loss functions aren't always that simple. In most cases, like deep learning, the loss function for high dimensions is very complex. Even for a simple 2D perceptron that takes 2 inputs and uses the sigmoid function as the activation function, the shape of the MSE loss function is complex. As you can see here, even for a simple perceptron with 2 inputs, the MSE loss function can be complex like this. For deep learning models with high dimensions, the loss function graph is much more complex. So it's usually very hard to find the derivative of such a complex function and compute the point where the slope is 0. That's why we need algorithms like gradient descent. You don't need to know all this math, but according to this proof, the essence of gradient descent is that the reduction in the loss function error is ultimately proportional to the slope of the loss function. If we represent this in a more visually concise notation, it can be simplified as follows. I must say, even without understanding this process, there's no hindrance to grasping gradient descent. But this last formula nicely captures the essence of gradient descent. This del C represents the slope at that point. So delta W is the same size as del C, but in the opposite direction, which means negative del C. This is because delta C becomes the largest when we set delta W to negative del C. This is why it's called gradient descent, because delta W is decided by the gradient or slope. By adjusting the value of delta W, we can gradually reach the lowest point. That's the core of gradient descent. Lastly, let's look at the formula for updating connection weights using gradient descent. In our last video, we learned the formula for updating perceptron connection weights. The key idea of this formula was that the bigger the input value, the more we change the connection strength to find the best parameters. The weight learning method using gradient descent is conceptually the same. The formula is: the larger the gradient of the loss function, the greater the change in connection strength. If we expand the formula further, it is as follows. Remember this formula, as it will be crucial when we explain backpropagation next time. Like the perceptron adjusts connection strength based on input value, gradient descent adjusts new connection strength based on the slope of the loss function. While perceptrons change connection strength based on the relationship with input value, gradient descent changes new connection strength based on the relationship with the loss function slope. Initially, we changed connection weights based on input values. But now we change them based on the slope of the loss function. This method is more efficient and advanced. Researchers are still trying to find better ways to find the best connection weights. Of course, gradient descent isn't perfect. One big problem is the local minima issue. More importantly, while human brains do learn gradually like this, there are also aha moments where they understand something instantly. Undoubtedly, some human learning is gradual, like learning a foreign language. But humans also learn through intuition and sudden realizations. Currently, in deep learning and AI, there's no learning theory that implements this intuitive human ability. To build machines that think like humans, we might need innovations that go beyond current learning theories. I hope someone watching this video can lead such a revolution. How was today's lesson on gradient descent? It might have been a bit challenging, but thank you for sticking with me. Next time, we'll cover one of the most important inventions in neural network history: the backpropagation algorithm. We appreciate your engagement and look forward to exploring further with you in the next session. Until then, farewell. Your interest and love for this channel help a lot in preparing these lectures, so please don't forget to hit the like and subscribe button.